This video will cover Chapter 4 of the Cisco curriculum. Chapter 4 is mainly about TCP and UDP, which both operate at the transport layer. TCP is part of TCP/IP, which is needed to communicate on the internet. The primary duties of the transport layer are segmentation. With segmentation, we are taking our message and breaking it up into smaller parts. Think of downloading a music file or a movie file. Those music files or movie files can be rather large. And instead of taking that whole chunk of the message and downloading it onto your computer, it's better and easier for us to segment it or break up that message into smaller parts. When you're watching this video right now, instead of taking this entire video and dumping it onto your computer, we have segments and parts of that video that get sent to your PC. The transport layer is also responsible for the establishment of end-to-end operations, the transport of segments from one end host to another end host, and flow control provided by sliding windows. We also use reliability with sequence numbers and acknowledgements at the transport layer. That's only with the TCP protocol. This slide here is going to compare and contrast TCP and UDP. And what you're going to notice is that they're kind of opposites for protocols. For example, TCP is connection oriented. With TCP, you make sure that the receiving host is available and can accept packets before sending the data. Because of this, it's considered reliable. Where UDP is just a best effort type of delivery. It just goes and it sends the message, does not do a three-way handshake or attempt to connect the receiving device before sending the message. Because of this, it's considered unreliable. With TCP, we're going to divide our outgoing messages into segments, and we're going to reassemble those messages at the destination station. We will resend anything that's not received. So if we notice one of those segments has not been received, we will resend that data. Once we get all of the data, we reassemble all of those segments into the whole of the message. Where UDP, on the other hand, does not retransmit the data if it does not make it there. There's no error checking involved, does not reassemble incoming messages, uses no acknowledgements or no flow control. We take a look at a TCP packet. It's a lot larger than a UDP packet. There's a lot of different things that are involved here. What I'm mainly concerned about that you know inside of a TCP packet are the source port and destination port, and I'll be talking about ports here in a little bit. The sequence numbers, acknowledgement numbers, and the window size. We also have our data, our actual data in there, but we have a lot of overhead with this packet. And the reason why we have a lot of overhead is so we can make sure that the message is delivered, we make sure that's reliable, we make sure that it can be reassembled in the correct order once it's received. Here's the UDP packet on the other hand. Very small, not a whole lot of information in there. Still has the source port and the destination port, but that's really about it. Again, UDP is connectionless, no windows, no acknowledgements. Error processing and retransmission must be handled by other protocols like the application layer. If you have ever tried to surf the internet and you type in a web address and you hit go and no page pops up, and then you hit refresh and then it does pop up, that's UDP at work. DNS uses UDP, so it's connectionless. We have no way of ensuring the data gets there. Well, what's happening is when you hit enter to go to that website, the message never made it there. The DNS message never made it there. So the way in which we ensure that it does get there is we hit the refresh. So we're responsible for that error checking, and we're responsible for the retransmission of that data. Whereas if DNS used TCP, it would resend the data until that web page pulled up. That's not how it works. So UDP is connectionless, and no guaranteed delivery of the packets. We said that TCP is reliable compared to UDP. And some of the ways that TCP is reliable is through sliding windows, sequence numbers and acknowledgements, and also through the use of synchronization. We're going to talk about some of the ways these work. One of the ways that TCP is reliable is through sliding windows. Sliding windows basically means that the amount of data that we can send at one point in time can change, or it can slide. In this example here, the window size starts off as 3. We try to send 3 segments of data over to the receiving host. But if we take a look here, only segment 1 and 2 is received. So our acknowledgement that we send back over is 3. That is our expectational acknowledgement. The expectational acknowledgement means the number of the segment that we expect to receive next. So we try to send 1, 2, 3. We only receive 1 and 2. So our acknowledgement is going to be 3 because we need to get 3 back. And it's saying put the window size down to 2. We then send 3, 4, and 5. Only 3 and 4 makes it. So what we expect to get back is 5. Put that window size back down to 2. It's telling the computer you're sending too fast. Lower your window size. Finally, the computer listens and only sends 2 at a time, sends 5 and 6. It expected 5, so we sent 5 and then 6. Then we receive 5 and 6. Our expectational acknowledgement now is 7. We expect to see the 7th segment next. Window size is still 2. If you have ever tried to download something from the internet, what you may have noticed is the speed at which you're downloading fluctuates, and that's what's happening. Your computer may be saying, download slower, I'm busy processing some other things. Or the server you're downloading from might be saying, you know, I can only give you so many packets at this point in time, let's lower this window size. So that window size can fluctuate throughout the transmission process when we're using the TCP protocol, like FTP does when we're downloading a file. TCP also resends anything that's not received and supplies a virtual circuit between end applications. This virtual circuit is going to guarantee delivery and is going to make sure that the device is up and ready to accept packets from us. In order to do this, we do what's called a three-way handshake. And with a three-way handshake, we basically send over a sequence number and acknowledge that sequence number. This is some packets that were actually sniffed on the network, and host A is going to send over to host B, and we're going to do the three-way handshake to make sure that we can start sending data reliably. So this host over here is going to send his sequence number, and his sequence number happens to be 12,952. So he sends over 12,952, and in order to acknowledge that number, we just add 1 to it. So what he sends back over is 12,953. So when we receive 12,953 back over on this end, we know we have been acknowledged. We sent over our number, he incremented it by 1, we received that back. Host B needs to send over his own message as well. So he sends over a message that has a number of 2,744,080 in it. So what host A is going to do now is take that 2,744,080 and we're going to add 1 to it. So we add 1 to it, send it back over. We see that our number has been incremented by 1. We know we have been acknowledged. We have now completed that three-way handshake, and we can assume that our packets are going to make it over there reliably. One thing I wanted to mention with the sliding windows is the numbers in the examples in the book and in this slide are very small. The window size in this example is 1. In an actual packet, if you look, the window sizes are going to be much larger, in the thousands. In this particular example, if we had a window size of 1, we can only send 1 segment at a time before we'd have to be acknowledged. If we relate this to humans communicating, it would be like saying 1 word at a time and having to be acknowledged with every single word that you send before saying the next word, which would make communication take a very long time. Another way in which TCP is reliable is through sequence numbers. We take all of these segments and we send them out on the network, and there's no guarantee that these segments are going to be received in the same exact order in which they were sent. We know that they'll make it there, but we may receive segment 1, 2, 5, 6, 10, and then later go get the segments that we missed. Because of this, we have to have a way in which we can reassemble these segments in the correct order and make sure that everything is there. And the way in which we do this is through sequence numbers. In the lab for this chapter, I'm going to have you guys sniff some packets. And when you sniff those packets, if it's a TCP packet, you'll be able to see these sequence numbers on each packet along with the acknowledgments and sliding windows and whatnot. TCP uses PAR, or positive acknowledgement and retransmission. This is how we guarantee the delivery of our data. When we send our data, we start a timer and we wait for the acknowledgement back. That's an expectational acknowledgement. So if we send packets 1 through 3, we will start a timer and we'll wait for that expectational acknowledgement back. If we never get an expectational acknowledgement back, we know that those segments have never made it to the destination. So then we will resend that data. So if the timer expires before the source receives an acknowledgement, we will just retransmit the data again. This happens with TCP. Remember that UDP does not use any windows or acknowledgments or any of these fancy things we just talked about. They just simply send the data, hopes that it gets there, and that's all they care about when we're using UDP. There's no guaranteed delivery of data, it's just best effort. Port numbers. Port numbers are brought up in this chapter as well, and port numbers are a very important topic to be made aware of. Port numbers are essentially used to keep track of different conversations on our network. Think about using your computer on a daily basis. You may have a web browser open, you may be downloading a file, you may be checking an email and playing a game all at the same time. Well, how does our computer know which packets are destined for which application? Well, the way it knows is by looking at the port number. For example, if your computer receives a packet from the network that has port 80 in it, it knows to send that packet to your web browser because HTTP in your web browser uses port 80. And if it receives a message with port 25 in it, it knows to send that to your email application because port 25 is for SMTP, Simple Mail Transfer Protocol. So by looking at the port number, our computer is able to tell where that packet is destined, and it's able to keep track of all these different things that are going on our computer and all the different communication that originates to and from those programs on our computers. There are some standard port numbers, and port numbers 0 through 1023 are considered well known and are used by specific programs. For example, port 80 is registered to HTTP and port 23 is registered to Telnet. Those will never change. And if you take a look at this link that I have here on the slide, you can see which port numbers are registered to which programs. We also then have registered ports, which is ports 1024 to 49151. If you're an application programmer and your application is going to communicate on the network or on the internet, you may have a registered port number. For example, if you play a game such as World of Warcraft or Halo or whatever it happens to be on your computer or on your gaming console, those are going to have ports that are registered to that specific application. So let's pretend you like to play Halo online, and Halo uses port 2302 and 2303. Those port numbers are registered to the Halo application. So if you were a programmer and you needed port numbers to be assigned to your specific program, you could go and try to register those with the IANA. If you do not have a registered port or you're not using a well-known port, you will just be assigned a dynamic port number, just a randomly generated port number that can be used to originate the data traffic. In this example here, we have a Telnet client that wants to communicate with a Telnet server. And what happens here is we have a port number that gets dynamically assigned as 1028. And 1028 then gets sent to 23. So 1028 becomes our source port, that's who it's originating from, and it's going to go to port 23, which is Telnet. Well, now when that server wants to reply back to us, it's going to use the destination port of 1028 because that's who it came from. And it's going to use the source port of 23. So now it's coming from the Telnet server and going to the client. So along with their IP addresses and MAC addresses, we now have port numbers that are used for a communication process. Take a look at this example. Let's pretend that we have two web browsers open. Well, if we want to communicate on the web, we use port 80. So in this example, they have Cisco open on this web browser and Cisco open on this web browser. So same exact page, coming from the same exact computer, coming from the same exact application. If I were to click on a link over here, how does the computer know whether or not to open that link on this browser page or on this browser page? Well, that's where it uses the source port. Who is that coming from? If I click the link over here, even though we're both going to port 80, this one's coming from port 1031 and this one's coming from port 1030. So we have to use that source port and the destination port in combination to know who we're coming from and where we're going to. In this example here, we have two clients. Both of these clients are going to connect to a telnet server. So when they connect, they're going to all be using port 23. We are going to destination port 23, which is telnet. Well, when we reply back from the telnet server to the client, what we notice here is that source port happens to be the same on these two clients. The source port that was dynamically generated happened to be generated by the same. So how do we know exactly to send it to client 1 or to client 2? Well, we have to use a combination. We use our port numbers to keep track of the specific conversations. We also use our IP addresses and our MAC addresses to differentiate between the specific hosts. Some of the port numbers that I will expect you guys to know are port 23 for telnet, port 25 for simple mail transfer protocol or SMTP, port 53 for DNS, port 80 for HTTP, and port 443 for SSL or secured HTTPS. That is all for this video on Chapter 4. I encourage you guys to read through the chapter. Again, the main topics are TCP, UDP, the transport layer, and port numbers. Thanks for watching.